Okay, so let's look at some conceptual examples here. First, we have a box against a wall. So we know from experience that if we want to hold something against a wall, do you think it's a mystery box? I think it's a mystery box.
It should be a mystery box.
Oh, but I'm not in my draw program, so even though I can draw, it's not going to show up. It's a mystery box. We don't know what's in it. It has mass M and some unknown M. We know if we push on it hard enough that it's not going to slide down. Well, why is that? Well, remember, the normal force is just the force between any two surfaces. And so in this case, the force is between the box and the wall, and the normal force is going to be perpendicular. So the normal force is the force, in this example, pushing to the left. So we know we're applying a force F. Our box is not accelerating into the wall. It's also not accelerating out of the wall. The wall is not providing a normal force pushing it out of the wall. So the normal force has to equal the force that we're pushing. Now we want to keep it holden. We want to hold it in place, keep it beholden to the wall and to us for not falling, because it's beholden to us because we're keeping it from falling. So in order to not fall, there has to be a force up, because there's always the force down, mg. So if it's not going to move downward, if it's not going to accelerate downward, there has to be a force up equal to mg if it's going to stay in place. The force due to friction is the coefficient of friction times the normal force. Well, okay, we're providing a normal force. So what's happening to keep this box from falling? Our pushing is providing sort of the normal force, and then that normal force times the coefficient of friction keeps the box from sliding. And if you think about it, just try to imagine if you had a wall with a rough surface, it'd be easier to push to keep it from falling than if you had a completely smooth surface. You'd have to push harder. Looks like there's another conceptual example here. Okay, so our little sister wants a ride on her sled. Oh, right, we use sleds a lot in Louisiana. Okay, if you are on flat ground, which we do have in Louisiana, will you exert less force if you push or pull her? Assume the same angle in each case. So in the first one, we're pushing from behind, and in the second one, we're pulling. Okay, so y'all speak loudly into the microphone. What do you think the answer is without reading the answer, which happens to be up there on the screen?
I didn't see
Yes.
We should pull it.
Why should we pull it?
Because if we exert force on the ground, that's going to increase friction.
How?
We're pushing down on it, which increases the force down to the ground, which is going to increase the normal force.
Normal force. Yeah. So if we push down, we're adding a component that's pushing into the ground, and so that is going to make the normal force bigger and make friction bigger. So we'd have to apply a bigger force if we're pushing and a smaller force if we're pulling, because if we're pulling, what are we doing to the normal force?
Reducing it by essentially making the object lighter.
Yeah, we're reducing it because we're reducing the force between the two surfaces. Okay, so let's take a look at this example now. We have a 10 kilogram box is pulled along a horizontal surface by a force Fp of 40 newtons applied at a 30-degree angle. This is like our example of 411, except now there's friction, and we assume a coefficient of kinetic friction of 0.30, and we're calculating the acceleration. Alright, so let's take a look at our 10 kilogram box. Mystery box, we don't know what's in it. And we have a 40 Newton force applied at a 30-degree angle. and that force is 40 newtons. What other forces do we have acting on this box?
Gravity down.
Yeah, we have gravity down,
Normal force up.
normal force up,
And the friction to the left of the picture.
And-
You're viewing this right side up.
and the friction to the left, which they tell us is kinetic friction. Now, I always draw a picture first, and then I'll go ahead and draw a free body diagram, even though our free body diagram will essentially look exactly the same. So I have the normal force up, force due to gravity down. I have some friction to the left. I don't know how much friction I have just yet.
Bothering you that vector's not broken up into components.
Oh, isn't it bothering you that vector's not broken up into components? Well, let's do something about that. Okay, so we want to break that vector up into components. So we'll do that right now.
Yay.
I thought I changed it to red. Oh well, won't worry about it. Oh, I changed it to light. Okay, we know that's 30 degrees. We know this side is 40. So what's this side right here? 40 sine 30.
Which just so nicely happens to be 20.
Which so nicely happens to be 20. This side, unfortunately, is not as nice. So 40 cosine 30.
34.
Can we use a radical?
No. What do you have?
34.64.
34.64 newtons. Notice we have actually one more significant figure here than we have in the problem. That's probably a good idea to keep that as you work through, and then you can round to the correct number of significant figures at the end. Okay, so let's take a look. Remember, horizontal and vertical act separately. So horizontal, vertical, they act separately.
Again?
Okay. Whoa. Wonder where that came from.
Oh, I think I know why it's not red.
Why is that?
Because the color pick thing is in the top right corner, so it's black.
Well, oh. I see. I wonder.
Right now I can't tell.
Yeah.
Oh, poor Connie.
Precisely.
I don't understand why they didn't make an eraser that will completely erase something in the first try.
Oh, they do. I just don't know where the icon is for it right now. So, but they do have such.
I think
It
you
is.
should click that little circle under soft eraser.
Well, not right now.
It says click me.
Oh, it does say click me. Well, to keep that from distracting us. Okay. All right. So our horizontal forces. We have our applied force, but just in the horizontal. Our applied force is to the right. We'll call that positive of 34.64. We have our force, our kinetic force of friction. That's to the left. We don't know what it is yet, but we do know it's mu k times the normal force, and it's to the left, so we'll call that negative. We also know what mu k is. Mu k is 0.30, so it's 0.30 times the normal force. Okay, now let's take a look at our vertical. Oh, we do have some acceleration. Let's go ahead and write that. So F net equals mass times acceleration, or the mass times acceleration equals 34.64 minus 0.30 n. We also know our mass is 10, so 10a equals 34.64 minus 0.30 n. Oh, look, I used n for my normal force instead of Fn. Oh, well. Okay, so now let's look at our vertical. What forces do we have vertically? We have Fg, the force due to gravity, which is mg, which is 10 times 9.8, or 98 newtons. We also have our normal force, which we don't yet know, but we do know that our net force equals our normal force, which is up, minus our force due to gravity, which is down, which is Fn minus 98, and that equals ma. Now, is our box accelerating in the vertical direction? Notice this is our vertical acceleration, this is our horizontal acceleration. They're different. This is our F net horizontal, this is our F net vertical. They're different. So, is our box accelerating in the vertical direction? No. So we'll say 0 equals Fn minus 98, or F... Yeah. Oh, it's not. It's not. Oh, thank you. That's why it's so good to have other people here. Yeah, look, that was wrong. 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 Yeah.
Edit that out. Just ignore it.
Yeah, okay. Wrong. Okay, yeah, there is another vertical force. So I only put that one in. So stop me sooner if I make a mistake like that.
Sorry, I just noticed.
Okay. Yeah, that was the whole point of this problem. That was the whole point of this problem, was we have a different normal force. Okay, so we have Fn, which we don't know what it is, but we also have an applied force, a vertical applied force, which is up, which is 20 newtons. So now, if we look at our F net is going to be the normal force up plus 20 up minus the force due to gravity down, which is 98. Now, it still is true, that part was not wrong, that our net force is still ma, which is 0. And 0 equals Fn plus 20 minus 98, which is negative 78? Yes?
Yes.
Okay, so Fn equals 78 newtons. Okay, so now that we know what this is, let's go back over here, and we have 10 times the horizontal acceleration equals 34.64 minus 0.3 times 78. So we have, oh, cool. Okay, so 34.64 minus 0.3 times, what was it, 78?
Yes.
Times 78 equals, and then divide that by 10, so we get 1.124. So our acceleration equals 1.124 meters per second squared.
Which is actually going to be just 1.126.
Yeah, to correct significant figures, 1.12 meters per second squared.